Every time a computer finishes a specific task, it immediately and violently destroys all the local memory it just used to do it.
Right, just totally wipes it clean.
Exactly.
Yeah.
It is a scorched earth policy happening millions of times a second inside your machine. It's relentless. It's absolute. So keep that image in your head.
Yeah, you really need to internalize that visual for what we're about to do today.
Because if you are listening to this right now, you are staring down the barrel of a major technical assessment on scripting and programming. Specifically, we are looking at Chapter 6 of your notes, which covers user-defined functions.
And look, we do not have time for any casual banter today, and honestly, neither do you.
No, absolutely not. This is an intensive, high-yield cram session custom-tailored for your exact syllabus.
Oh.
The mission today for this deep dive is absolute mastery of this chapter.
We are going to get you completely ready for this.
I mean, I am looking at a desk just totally covered in your study materials. We've got detailed flowcharts, coding snippets, execution animations, variables, tables. We're going to tear through all of it.
Concept by concept, right until the underlying logic is basically second nature to you. But to truly ace this exam, you have to undergo a fundamental shift in your mindset right now.
Yeah, because rote memorization is it's not going to cut it here.
It's a guaranteed path to failure on this specific test. The assessment isn't going to just ask you, like, hey, what is a function? It's going to demand that you understand the execution flow.
You actually have to be able to visualize how the computer's processor jumps around the code in real time.
Precisely. You have to see how it allocates and then, like you said, completely annihilates memory. And crucially, you need to spot the logical traps that the exam raters have deliberately laid out.
Oh, they definitely want to exploit your assumptions.
They do. So we are going to build an airtight mental model for you today. When you sit down for that test, the code is going to read as clearly as a map.
Well, let's start building that map right now with the most fundamental building block in all of this material, the anatomy of a function.
Let's do it.
So in the absolute simplest terms provided in your notes, a function is defined as a named list of statements.
Right, which sounds completely harmless on the surface.
It really does. It's just a list. But looking through your study materials, there is a massive, impenetrable dividing line drawn between a function definition and a function call.
Yeah, they treat them as two entirely different universes, and you have to do the same. The distinction between those two is the foundation of everything else we'll discuss today.
It's literally the very first place students crash and burn on the exam, isn't it?
It is. So, let's bring it down. A function definition consists of the new function's name, which can be any valid identifier allowed by the language, and the actual block of statements that make up its internal logic.
Okay, so think of the definition as an architect drawing up a highly detailed set of blueprints for a house.
I like that analogy. The architect is laying out exactly where the plumbing goes, how the electrical is routed, all the precise dimensions of every room.
Right, but drawing a blueprint, no matter how detailed it is, doesn't magically conjure a physical house out of thin air.
Exactly. The blueprint is just potential. It's sitting there on a desk, completely inactive.
I mean, I could write a function definition that calculates the trajectory of a rocket to Mars with like 10,000 lines of the most complex math imaginable.
But if all you do is define it, the computer doesn't actually do any of that math.
The program's active execution just ignores it entirely, right?
It absolutely ignores it. Defining a function does zero actual work. It consumes no processing power to run those internal statements because they aren't being run. They're just registered for potential future use.
So what actually breathes life into those blueprints?
That would be the function call. A function call is the explicit invocation that commands the processor to actually execute the statements inside the definition.
Okay, so knowing how these exams are structured, I can easily see the trap here.
It's a classic one.
They're going to give you a massive block of code. At the very top, there will be this beautifully written, highly complex function definition. It'll have loops, complex math. It'll look incredibly important.
Yep. And then somewhere in the questions, they will ask you something like, how many times does this specific statement inside the function execute when the program runs?
And if you scan the rest of the main program and realize that function name is never actually called, what's the answer?
The answer is always 0, period.
But students will waste 5 minutes manually tracing all the math inside that function definition.
Right, trying to calculate a final value, completely missing the fact that the function was never even invoked. So rule number 1 for the exam, Do not count the lines inside a function definition as execution steps unless you see a distinct, explicit call invoking that specific name elsewhere in the code.
Okay, I want to look at the real-world physical operation of this, because the notes provide a great flowchart for a program called Print Pizza Area.
That's a really good example to trace.
Right, so every single program's execution begins in a centralized starting point, which is usually called the main function.
Correct. Always start tracing at main.
So imagine we are tracing the program, we are cruising along in main, executing statements one by one, and suddenly we hit a rectangle in the flowchart that just says Print Pizza Area with open and closed parentheses.
Okay, so what is the processor physically doing at that exact millisecond?
Yeah, what's the actual mechanism there?
It executes what is known as the execution jump. When the program hits that call, it literally halts its current downward progress through main.
It just stops.
It completely pauses. It places a bookmark, essentially logging the exact memory address of where it currently stands. Then the processor's focus leaves main entirely and jumps over to the first executable statement inside the Print Pizza Area function's definition.
Wherever that happens to be stored in the code.
Exactly.
Let me try to map this to a physical analogy to make sure the mechanics are locked in for you listening. Is a function call basically like sitting in your living room watching a movie and suddenly you decide you want popcorn?
I see where this is going.
So you hit pause on the remote, the movie completely freezes, you physically leave the living room, so that's the execution jump, right?
Right, you're leaving main.
And you go into the kitchen. The kitchen is the function definition. You run through a very specific sequence of statements. You get the bag, you put it in the microwave, punch in 2 minutes, wait, pour it into a bowl.
And that entire time, the living room is frozen.
Exactly. Nothing is happening on the TV. And then, when you hit the end of your popcorn routine and walk back out, you sit down, grab the remote, and press play on the exact timestamp you left off.
That sequence of events maps perfectly to the processor's behavior. The computer handles the jump with that exact same strict, unyielding sequence.
It's a really rigid process, isn't it?
Totally rigid. Let's trace the execution animation provided in your materials to see the digital equivalent of making that popcorn.
Okay, let's walk through it.
So we start in main. The program hits the call Print Pizza Area. The movie pauses. The processor jumps to the function. Now, inside the function, it begins evaluating the local statements.
Like getting the popcorn bag out.
Right. First, it assigns a constant value, setting PIVAL to roughly 3.14159. Next statement, it assigns a variable pizza diameter, the value of 12.0.
Makes sense.
Then it calculates the pizza radius by taking that diameter and dividing it by 2.0, storing the result, which is 6.0.
Okay, I'm following the math.
Next, it runs the core mathematical formula pi times radius. It crunches those numbers and assigns the final result, roughly 113.1, to a variable called pizza area.
So the math is done.
Yep. And finally, it hits a block of output statements, printing the text to the screen. 12.0-inch pizza is 113.1 square inches.
So it followed the blueprint perfectly. The popcorn is made.
The task is complete, but the mechanics of how it ends are just as important as how it began.
What happens next?
After that final output statement prints to the screen, the flowchart hits an explicit end statement. At that exact millisecond, the function's lifecycle is over.
And it jumps back.
The execution jumps strictly back to the original bookmark it left in main. The movie unpauses. The processor looks for the very next line of code beneath the function call in main and continues its downward execution as if it had never left.
But wait, what about all the data it just generated? I mean, it created a PVAL, a pizza diameter, a pizza radius, and a pizza area.
Now we get to the really tricky part.
Yeah, because your study materials introduce a concept here called a local variable, which is defined as a variable declared within a function, making it accessible only within that specific function.
This is a major architectural rule of programming, and honestly, it forms the basis for some of the most difficult questions on your assessment.
So those variables like pizza diameter, pizza area, they are entirely local to the Print Pizza Area function. Yes, they do not exist outside of it. If you try to write a line of code down in main, right beneath the function call, that says something like output pizza area, the entire program will crash and throw an error.
Because main has absolutely no idea what pizza area is.
None. It's a completely foreign concept to the main program. From the perspective of main, pizza area was never created.
Going back to the analogy, it's a localized piece of reality, isolated entirely within the kitchen.
Exactly. The living room doesn't know about the microwave timer. It doesn't know about the popcorn bag. It only knows that the movie was paused and unpaused.
For you, the listener, when you were sitting in the exam room and you encounter a variable tracking question where they give you a block of code and ask what the value of a specific variable is at the very end, you have to respect this physical isolation.
You really do. You need to draw a hard line down the middle of your scratch paper.
Keep strict, separate columns for the variables that exist in main and the variables that exist in the function. If you let them cross-contaminate in your head, you will confidently choose the wrong multiple-choice answer.
The isolation is absolute. But, of course, a program where the living room and the kitchen can never interact isn't very useful.
Not at all.
Right, because if our print pizza area function just calculates a 12-inch pizza every single time it gets called, it is a fundamentally useless piece of code. It just does the exact same static math forever.
It's just a broken record.
To make a function powerful, we have to be able to change its behavior dynamically. We need to be able to send data from the living room into the kitchen.
Which brings us to the next major conceptual hurdle, controlling behavior and the crucial distinction between parameters and arguments.
Yes. If there is one terminology mix-up that consistently ruins assessment scores, it is conflating parameters and arguments.
The exam writers know this is a weak point for students, and they will target it aggressively with trick questions. You need to permanently separate these two words in your mind.
So what's the official breakdown?
A parameter is a function input specified in a function definition. An argument is the actual tangible value provided to that parameter during a function call.
Let's ground this with a visual for the listeners. Think of a parking lot.
Okay, I'm picturing it.
The parameter is the empty parking space. It has a big reserve sign painted on the asphalt. It dictates the size of the car that can fit, and it holds a specific location, but it is fundamentally just empty space.
Right.
The argument, on the other hand, is the specific physical car that you drive into that space on any given Tuesday.
That is a perfect visualization. The parameter is the concept of the space. The argument is the occupant.
So when you look at a function definition, you might see something like function print pizza area, float pizza diameter.
In that blueprint, pizza diameter is the parameter. It is the empty parking space.
It is essentially a variable declaration waiting for data.
Right. It's saying, hey, I have reserved a space in memory for a floating point number, and I will call it pizza diameter. But when you are down in main, and you actually initiate the execution jump by writing print pizza area 12.0.
The 12.0 is the argument. It is the physical car driving into the lot.
Yes. Now, let's trace the actual physical memory operation that happens in the background when that call is made. Your notes feature a very specific animation detailing this, which means it is highly testable material.
Let's hear it.
When the program hits the call, print pizza area 12.0, the processor halts main and allocates a brand new specific memory location for the parameter pizza diameter.
It physically pays the parking space.
Exactly. Then the parameters immediately assign the value of the argument. So the number 12.0 is copied into that newly created memory slot.
And then it starts running.
Once that is done, the function begins executing its math using that 12.0 wherever pizza diameter appears in the code.
It runs the math, it prints the area, and then it hits the end statement. And this ties back to the scorched earth hook we started the deep dive with.
It sure does.
What physically happens to that parameter's memory space the moment the function ends?
It is utterly deleted from the system's memory. This is the exam trap I need you to be hyper aware of.
Okay, pay attention to this part.
Upon return to main, the parameter is erased, the parking space is bulldozed, the memory address is freed up for the operating system to use for something else.
It doesn't just go dormant, it is gone.
Completely gone. Students constantly fall into the logical trap of assuming that because they went through the effort of passing 12.0 into a parameter, that parameter must somehow hang around in the computer's background memory after the function concludes.
Like it's holding onto that value just in case it's needed again.
Right, but it does not. The local scope is violently destroyed to optimize system resources. If main tries to reference pizza diameter after the function returns, it will crash.
Because pizza diameter no longer exists in the physical universe of the computer's memory.
Exactly. Now, let's push this syntax further because the exam is not going to just ask you about a simple single parameter function.
Right. What if the math requires more data? For instance, what if I want to calculate the volume of a pizza? I don't just need the diameter across the top. I also need the height of the crust.
Your notes actually show a function defined to handle this print pizza volume, 12.0.3.
Okay, so when you pass two numbers like that, How does the processor know which number belongs to which parameter?
Hmm.
Does it guess based on the size of the numbers?
The processor never guesses. It follows the strict rule of positional assignment.
Positional assignment, got it.
Let's look at the function definition for this scenario. It says function print pizza volume, float pizza diameter, float pizza height. The rule here is absolute and inflexible. The first argument provided in the call is assigned to the first parameter in the definition.
And the second argument is assigned to the second parameter.
And so on down the line. They are assigned strictly by their position in the parentheses.
So the 12.0 is the first argument, so it automatically slots into pizza diameter. The 0.3 is second, so it slots into pizza height.
Exactly. And the danger here is that the computer is obedient, not smart. It has no context for what a pizza actually is.
It just blindly follows the positions.
Right. If you, the programmer, made a typo in main and accidentally wrote the call backward as print pizza volume, 0.3, 12.0, the compiler wouldn't second-guess you.
It wouldn't throw a warning saying, hey, a pizza that is 1/3 of an inch wide and 12 inches tall is physically impossible.
It absolutely would not. It would simply assign 0.3 to the diameter, 12.0 to the height, and calculate the volume of a bizarre spaghetti noodle-shaped cylinder.
So on the exam, if they give you a code trace with backward arguments, you must trace the math exactly as the computer would, absurdity and all.
Trace what is written, not what you think makes sense. Now, let's look at the opposite end of the spectrum. I noticed a very specific syntax quirk in the materials regarding functions that don't need any inputs whatsoever.
Oh, yeah. If a function requires no parameters, the definition just has empty parentheses next to the name, like print greeting.
But the trap regarding zero-parameter functions isn't in the definition, it's in the call. If a function is defined with no parameters, the callback in main must still include those empty parentheses.
Wait, you cannot just write the word print greeting and expect the function to run.
No, it has to be print grading.
Why is the computer so pedantic about that? Why do the empty parentheses matter if there's nothing inside them?
Because without them, the compiler's parser gets confused. When the compiler reads the word print greeting without parentheses, it assumes you were trying to reference a variable named print greeting.
Oh, I see.
The parentheses act as the universal mechanical signal to the processor that an execution jump needs to happen. They are the trigger.
If you leave them off, the program doesn't know it's supposed to jump, and it will throw a syntax error.
Expect to see at least one multiple-choice question where the wrong answer is a function call missing its parentheses.
There is another really interesting layer to how arguments work that your notes highlight. Arguments do not just have to be flat, static numbers. You don't have to just type 12.0.
Right, an argument can be a fully fleshed out mathematical expression. For example, if you have a variable x that is currently holding the value 5, you can make a function call that looks like this print pizza area by 1.5.
So if you do that, what is the computer actually sending into the isolated kitchen? Does it send the literal characters x, 1, 5 foot to the parameter? Does the function have to figure out what that math means?
No, and this is a vital concept for tracing code. The computer must fully evaluate the expression before it passes anything across the boundary into the function.
Okay, so it does the math first.
The processor acts like a bouncer at the door of the function. It stops the execution jump temporarily. It looks at the argument by 1.5. It fetches the value of x, which is 5. It multiplies it by 1.5 to get 7.5.
And only then, once the expression has been simplified to a single final value,
Yeah.
does the bouncer open the door.
Yes, exactly. The value 7.5 is passed as the argument to the parameter. The parameter inside the function never knows that an equation took place. It only receives the final calculated result.
When tracing on the exam, always solve the math inside the parentheses of the call before you jump to the function definition.
Always.
Okay, so we have exhaustively covered how to get data into the function using parameters and arguments. We've sent the ingredients into the kitchen.
But that creates a massive logistical problem.
Right, which brings us to the next phase of our review retrieving data. If all the local variables and all the parameters are instantly and violently deleted the second the function hits its end statement, how does main ever find out the answer to the math we just forced the function to do?
That's the multi-million-dollar question.
If the kitchen burns down the second the meal is cooked, how does the waiter get the food back to the living room?
We rescue the data using the return mechanism. And mastering this requires dissecting two very specific terms that students often blur together: the return variable and the return value.
Okay, let's unpack this.
A function is able to send data back to the calling program by assigning a specific return variable with the return value right before the memory is wiped.
Let's look at the mechanics of this using the compute square flowchart from your chapter. We have a function named compute square that is designed to take a number and multiply it by itself.
It takes one integer parameter, which we'll call num to square.
But importantly, the definition also declares a return variable named num squared.
Right, so let's trace the full life cycle of a piece of data through this architecture. Down in main, we see an assignment statement, squared val equals compute square 7.
So first, the execution jump occurs.
The processor pauses main, jumps to the function, and passes the argument 7 into the parameter num to square.
Now we're inside the function's isolated memory space.
The math executes num squared, num to square, num to square. That is 7 times 7. The local return variable, num squared, is now holding the integer value 49.
The calculation is done, the flowchart moves to the next block, and it hits the end statement. The bulldozer is idling right outside the kitchen. What happens?
In the split second before the local memory is wiped, the value held inside the return variable is actively returned across the boundary.
It sneaks out just in time.
The function's execution completes, the local variables are destroyed, but that number, 49, is successfully smuggled back to main.
And here's the most important part of how you visualize this for the exam. The entire function call expression back in main, the actual text compute square 7, literally evaluates that return value.
It's basically magic. The computer essentially highlights the text compute square 7 and overwrites it with the number 49.
So the original statement in main, which was squared val compute square 7, effectively becomes squared val equal 49.
Exactly. The final value is successfully assigned to a variable safely inside main's memory space, and the program continues onward.
But looking at the rules for this return mechanism, I have to push back on the architecture here.
Oh, really? Why?
Because your notes highlight a massive, strict limitation. The text explicitly states a function can only return one item, not two or more.
Yes, the one-item limit.
If I am building a complex application, what if I genuinely need to calculate the area A and D, the volume of a shape, simultaneously? Or what if I'm making a video game and my function calculates a player's coordinates, which requires both an X and a Y value? Am I just out of luck because of this strict one-item limit?
This is a fantastic observation, and it brings up a critical difference between the educational framework you are testing in and broader software engineering.
Okay, so it's a test-specific rule.
Well, the technical rule of this specific scripting language and the rule you must follow to pass this assessment is strictly one return value. Period. If you see a true-false question on the exam that says a function can have two return variables, you must select false. Do not hesitate.
So how do professional programmers actually get around this bottleneck in the real world? They aren't just limited to returning a single number at a time, right?
They use architectural workarounds. If a developer needs two distinct, simple pieces of data, like area and volume, they might just write two completely separate functions and call them one after the other in main.
That seems a bit tedious.
It can be. But in more advanced, real-world programming languages, you can bundle multiple values into a single, overarching data structure. You might place the X and Y coordinates into a list, an array, or a custom object.
Oh, okay, I see.
Then the function returns that single collection. Technically, it is still only returning one item, one array, but that one item contains multitudes.
That's a clever workaround.
It is, but for the scope of your exam and the syntax provided in your notes, the rule is one distinct value. If a multiple-choice question tries to trick you with a function returning variable A and D, variable B, cross it out. It is a syntax error.
Good to know. And what about the opposite scenario? What if a function isn't meant to return anything at all?
That happens quite a bit, actually.
Let's look back at our print pizza area function from the very beginning. Its entire job was to calculate the math and print text directly to the screen. It didn't need to hand a calculated number back to main to be stored in a variable.
If a function does not return a value back to the caller, the blueprint must explicitly declare that fact, so the compiler knows not to wait for a package to be delivered.
How does it declare that?
In the syntax used in your materials, the first line of the definition must state returns nothing. For example, function print pizza area, float pizza diameter, returns nothing.
That specific phrase, returns nothing, sets up a massive exam trap highlighted in the notes regarding how expressions are evaluated.
Yes, and this requires you to combine two concepts we've just discussed. We established that when a function returns a value, the actual call itself evaluates to that value.
Right.
Because of that behavior, a function call often appears deeply embedded within a larger mathematical expression.
For instance, if we know the compute square 4 returns the number 16, we can write an expression in main that says 5 plus compute square 4.
The processor handles that perfectly. It
Yeah.
evaluates the function first, gets the 16, brings it back, and then adds it to the 5, resulting in 21.
But here's the trap that catches everyone working over. You cannot do this with a function that returns nothing.
You absolutely cannot.
So if I have a function called printval 9.0, and it is explicitly defined as returns nothing, I can't put it in an equation.
You cannot write a statement like y equals printval 9.0.
Because what on earth is the computer supposed to assign to y?
Precisely. There is no data coming back. The function just prints some text to a monitor and then vanishes. It returns a void.
The computer expects a tangible value to assign to y, and when the function hands back nothing, it triggers a guaranteed syntax error.
On the test, they will give you a list of assignment statements and ask you to identify which one is valid. If you see a returns nothing function used on the right side of an equal sign or added to a number or used in a greater than comparison, eliminate it immediately. It is invalid architecture.
Okay, let's take all these rules about expressions and push the complexity up to the absolute maximum.
Let's do it.
Your notes feature a section on nested functions. This is essentially the practice of putting a function call inside the argument, a parentheses of another function call.
Oh, this is where students really start to sweat.
The textbook gives a terrifying little example. Square. Inkby 2.3. When a student is sitting in a silent exam room, staring at this inception-level nightmare of nested parentheses, how do they trace the logic without panicking?
By falling back on a strict mechanical rule, read it from the inside out. Always, always start with the innermost set of parentheses.
So do not even look at the word square yet. Pretend it doesn't exist.
Ignore it completely. Tunnel down to the very center and look at Inkby 2. That is your starting point.
Right.
The computer must evaluate the innermost argument first before it can do anything else. The execution jump happens. The processor pauses main, jumps to the Inkby 2 function, and passes the argument 3 into its parameter.
Let's assume the function simply adds 2 to the parameter.
So it computes 3 plus 2, which is 5. The function ends, the memory wipes, and it returns that value, 5, back to the expression.
So now that entire inner block of text, Inkby 2 third ton out, visually disappears from the code and is replaced by the number 5.
Exactly. The complex outer expression has now simplified from square, Inkby 2.3, to simply square 5.
That looks way more manageable.
Now, the processor can finally handle the outer layer. A second execution jump occurs. It jumps to the square function, passing 5 into its parameter. The function computes 5 times 5, returning 25.
The final answer to the entire nested nightmare is 25.
If you trace it strictly from the innermost parentheses outward, step by step, rewriting the expression on your scratch paper at each stage, it is impossible to get wrong.
But if you try to jump around or hold the state of both functions in your head simultaneously,
Your mental call stack will overflow and you will fail the trace. Don't risk it. Write it down.
taking a step back from all these hyper-specific tracing rules, I want to address the elephant in the room.
What's that?
We have talked endlessly about pausing the execution, jumping to different memory addresses, managing isolated scopes, violently wiping local variables, and adhering to strict return limits.
A lot of overhead.
It sounds incredibly complicated and computationally expensive. This brings us to a conceptual section of your notes, the why behind program architecture. Why do programmers bother building this elaborate architecture of functions? Why not just write one long, straightforward, continuous list of code that executes top to bottom?
To understand the why, you have to realize that computer science isn't just about giving instructions to a machine. It is about managing human cognitive load.
Human cognitive load.
Right. The processor does not care if a program is 1 line long or 1,000,000 lines long. It will execute 1,000,000 lines of messy, tangled code just as happily as it executes a clean function.
But humans are the ones who have to write, read, debug, and update this code.
And human brains are incredibly bad at holding thousands of interconnected variables in working memory simultaneously.
Your study materials provide a perfect, stark visual contrast to illustrate this point. They show two different flowcharts for a program designed to convert a user's daily steps walked into calories burned.
The first example is a glimpse into the dark ages of programming. It shows the program written without any functions at all.
It is a massive, unbroken, 16-statement monolithic block sitting inside main. I'm looking at it now, and just glancing at the flowchart makes my eyes glaze over.
That's awful, isn't it?
It declares a huge, disorganized list of variables right at the top: steps walked, feet per step, feet per minute, steps per minute, cal per minute walking, minutes total, calories total, miles walked.
It's just a data dump.
And then it just dives into a dense, terrifying block of raw math. It's mixing the miles calculation right next to the calories calculation with input and output statements sprinkled haphazardly in between.
It is spaghetti code. If a bug occurs, say, the calories calculation is outputting a negative number, a programmer has to wade through all 16 statements, tracing every single variable, trying to figure out where the math went wrong, while actively ignoring the miles calculations that are tangled up in the middle of it.
It is an administrative nightmare.
Now look at the second example in your notes where the exact same program is written using functions.
The difference is night and day. Main is incredibly simple. It only has 3 distinct actions. First, it gets the user input for steps walked. Second, it calls put steps to miles, steps walked to output. Third, it calls put steps to calories, steps walked to output. That's the entire main program.
It reads almost like plain English. By glancing at main, you immediately understand the high-level purpose of the software without having to parse a single algebraic equation.
We call this process decomposing a program.
By abstracting those nitty-gritty, highly specific math details and hiding them inside their respective functional kitchens, main avoids getting bogged down.
The code becomes inherently readable, which makes it significantly easier to maintain and update in the future.
And this modular approach allows for a workflow that your notes heavily emphasize incremental development.
Incremental development, right.
Modular development is the philosophy of dividing a massive program into separate, bite-sized modules that can be built and tested completely independently and then integrated together later.
So incremental development is the actual physical process of executing that philosophy.
Yes. You write and test a few statements. You verify they work perfectly. Then you write and test a small amount more. You do not attempt to build the entire skyscraper at once.
You build one room, you make absolutely sure the electrical outlets work, you verify the plumbing doesn't leak, and only then do you move on to building the next room.
Exactly. And the primary tool programmers use to facilitate this incremental process is called a function stub.
A function stub is defined in the text as a function definition whose statements haven't actually been written yet.
The textbook shows a great example of this too.
Yeah, it shows function conf at kilometers to miles. But instead of doing any mathematical conversions inside the definition, there is just a single print statement that says, put fix may, convert kilometers to m to output.
A developer uses a function stub as a placeholder. It allows them to capture the high-level behavior of main and ensure the execution jumps are routing correctly before they dive into the agonizing details of getting floating point math perfectly accurate.
It's exactly like planning a cross-country road trip. You know you need to route through Chicago, so you put a giant pin on the map there, but you haven't bothered to look up the specific street directions yet. You are just outlining the overarching flow.
That's exactly how developers use them.
So hearing all this, I want to present a question that sounds exactly like how an exam writer would phrase a trap.
Hit me.
Do function stubs actually make the computer run the program faster?
That phrasing is a classic pitfall. Exam writers love to test if you understand who benefits from specific tools, the machine or the human.
So what's the answer?
Function stubs offer absolutely zero performance benefit to the computer's processor. In fact, technically, performing an execution jump to a stub that does nothing but print fix mess is slightly less efficient than doing nothing at all.
Oh, wow. I wouldn't have guessed that.
A key benefit of function stubs is not a faster running program. Their benefit is purely psychological and organizational for the human developer. Do not select any multiple choice answer that implies snubs optimize processing speed or reduce memory overhead.
Beyond organizing cognitive load, another massive tangible benefit of using functions is avoiding redundant code.
Yes, replacing redundant statements by writing the code once and calling it multiple times.
The notes highlight a very practical circle area example to drive this home. In the bad redundant version of the code, a programmer needed to calculate the area for a 12-inch pizza and a 14-inch pizza in the same program.
Right, so they manually wrote out pival equals 3.14159 and circle area 1 equals pival circle radius 1 circle radius 1.
And then, literally 3 lines later, they copy-pasted the exact same math again for circle area 2 and circle radius 2.
Which means if you suddenly realize you need more precision and want to change pi to 3.14159.265, you have to hunt down every single instance where you copy-pasted that formula and manually fix it.
If you miss even one, your software is mathematically broken.
Redundancy is the enemy of stable software. By abstracting that mathematical formula into a single circle area function, you only ever write the equation once.
If you need the area of 100 different pizzas, you just call the function 100 times.
If you need to update the precision of pi, you change it in exactly one place inside the function definition, and every single call throughout the entire program is instantly updated.
The skill of recognizing redundant logic and decomposing it into a well-named, highly specific function is a fundamental requirement of modern programming.
It really is.
But is there a limit to this? Is there a rule of thumb for how large a single function should be allowed to get? Because knowing human nature, I could easily see a lazy programmer just shoving 500 lines of unrelated code into a single function, naming it do everything, and defeating the entire purpose of modularity.
Your course materials offer a very specific, testable guideline regarding size. A function definition usually shouldn't exceed about 20 statements.
20 statements, got it.
If it is growing significantly longer than that, it is almost certainly trying to accomplish too many tasks at once, and it needs to be broken down further into smaller subfunctions.
Is that a hard rule? Like, will it crash if I write 21 lines?
No, to be clear, this is not a strict syntactical law. The compiler will not throw an error if you write a 100-line function. It will execute it perfectly. But the 20-statement rule is a core principle of good software architecture designed to maintain human readability.
So if a true-false question asks if a function must be under 20 lines to run, that is false. But if it asks for the general architectural guideline, 20 is the magic number.
Correct. Okay, we are in the home stretch of this cram session. Let's tackle the final, most advanced topic, complex execution.
Up until now, almost all of our examples have been extremely straightforward. The processor jumps to the function, does a couple lines of basic straight-line math, and comes back.
But functions aren't just dumb calculators. They're self-contained programs.
Which means a function can contain absolutely anything that maze can contain. They can execute highly complex internal logic, including branch statements, loops, and dynamically changing variables.
Let's walk through a real-world operation from the notes to illustrate how this logic flows. There's a flowchart for an eBay fee calculator.
The function is named eBay fee, and it takes a single parameter sell price. Its entire job is to determine how much of a cut the website takes from a sale based on a tiered, branching logic tree.
This is a textbook example of a tracing problem. You are almost guaranteed to see a flowchart exactly like this on the exam, and you will be asked to track the changing state of a variable as it moves through the branches.
Let's trace it carefully.
The function begins by initializing its return variable fee total equals 0.50. That 50 cents is the base listing fee. Everyone pays it, regardless of the item's price.
So before we even look at the branches, our local variable fee total is sitting at 0.50.
Correct. Then the execution hits the first branch in the logic tree if sell price equals 50.00. If the item sold for $50 or less, the fee is the base fee plus a flat 13% of the selling price.
And the assignment statement inside that branch reads fee total equal fee total plus sell price 0.13.
Let's say I'm tracing this for an exam question where the call was eBay fee 20.0. So 20.0 was passed as the argument for sell price. A classic exam question here would ask, how many assignment statements for the variable fee total will execute for the call eBay fee 20.0?
To get the answer, you must trace the processor's path literally.
First, the initialization statement fee total equals 0.50 executes. That is one assignment. Next, the processor evaluates the if condition is 20.0 less than or equal to 50.00.
That evaluates to true.
So execution enters that specific branch. The statement inside executes, taking the existing fee total, adding the calculated percentage, and assigning the new value back to fee total.
That is the second assignment statement.
Because an if branch was satisfied, the processor skips all the other else if branches, finishes the function, and returns the value. The answer to the question is 2.
What if the item sells for significantly more, say $100?
The code contains an else if branch to handle higher tiers. Else if sell price equals 1,000.00. If it sold for up to $1,000, the website charges the base fee plus 13% on the first $50 plus only 5% on whatever amount exceeds 50.
But the math itself is less important than recognizing the structure of the execution, right?
Exactly. Because this is an if-else chain, the processor will only ever enter and execute one of those math branches per function call.
The exam will try to trick you by asking you to trace a path where multiple branches execute.
That is impossible. You must evaluate the logic path strictly based on the specific argument provided, follow that single branch to its conclusion, and ignore the rest of the code.
Tracing a single function is hard enough, but this brings us to a final, crucial architectural reality in your notes. It's a concept that completely breaks the mental model of students who haven't fully grasped the mechanics of the execution jump.
This is the big one.
We keep talking about jumping from main to a function and back, but main is not some magical, omnipotent entity. Main is simply the first function called when a program executes.
The reality is, any function can call any other function. The ability for functions to call other functions is what allows software to scale to millions of lines of code.
The ZBooks notes use a pizza calories program to demonstrate this architecture. When the program runs, main begins executing. It asks the user for input and assigns it to pizza diameter. Then, main issues a call. Put pizza calories, pizza diameter, to output.
The execution jump occurs. The processor pauses main and jumps over to the pizza calories function.
But once we are inside pizza calories, things get complicated. To figure out the total calories, the function realizes it needs the total area of the pizza. It doesn't want to do that complex math itself.
So right there in the middle of pizza calories, it executes a statement, total calories equals circle area, pizza diameter, calories per square inch.
It issues its own execution jump. The processor now pauses pizza calories, which is already a paused state away from main, and jumps over to a third function, circle area.
Let me bring in an analogy here to map this hierarchy, because the visual of jumping deeper and deeper can get abstract. Think of a corporate office.
The CEO of the company is the main function. The CEO needs a comprehensive report on pizza calories.
The CEO delegates the entire task to a mid-level manager, which is our pizza calories function.
The CEO kicks their feet up on the desk and goes on pause. The manager starts working on the report, but quickly realizes they need a highly specific mathematical equation solved to finish it.
The manager doesn't want to do the math either, so they delegate that specific task to an intern, the circle area function.
The manager goes on pause. The intern goes to their desk and starts crunching the geometry.
This corporate hierarchy analogy is perfect for pointing out the final, most devastating exam hazard in this chapter. Let's trace the return path. When the intern, circle area, finishes their geometry math and gets the final number, who do they hand the report back to?
They hand it back to the manager who directly asked for it.
Exactly. The intern reports back to pizza calories. They do not bypass the chain of command and hand the report directly to the CEO.
But under the stress of an exam, students constantly fail nested execution tracing questions by making a massive assumption.
They assume that every single time a function hits an end statement, the processor automatically jumps all the way back to main. It does not.
Execution strictly returns to the exact location that issued the call.
Circle area finishes and returns its value to pizza calories. Pizza calories receives the data, unpauses, finishes computing the total calories, hits its own end statement, and then returns its final calculated value back up the chain to the CEO main.
You have to follow the chain of command step by step, both going down into the functions and coming back up. You can't skip rungs on the ladder.
The computer manages this using something called the call stack. It is a literal stack in the system's memory that meticulously remembers exactly who called who and in what order, placing a new bookmark on top of the stack for every jump.
When you are tracing complex code on your scratch paper, you must replicate this stack visually. Draw arrows.
If main calls function A and function A calls function B, draw an arrow from B pointing back to A. When B ends, your eyes must follow that arrow back to A, not to main.
If you master the call stack, you master execution flow.
Yeah.
All right, take a deep breath. We are out of time and you have survived the cram session.
We made it through.
Let's do a rapid-fire wrap-up to solidify everything we've built. We have covered a massive amount of ground today. We established that a function definition is nothing but an inactive blueprint. It consumes no execution steps until a function call physically invokes it.
We tracked the mechanics of the execution jump, proving that the calling function completely pauses its progress while the subfunction works.
We broke down the vital difference between a parameter, which is the empty reserved parking space in the definition, and the argument, which is the specific numerical car you pass into it during the call.
We covered the strict rules of returning data. Remember, only one item can ever be returned, and if a function explicitly returns nothing, attempting to use it in a math expression is a guaranteed syntax error.
We proved that function stubs exist purely to aid human readability and incremental development, offering zero-speed optimization to the processor.
And finally, we traced complex internal branch logic and nested function calls. Establishing the golden rule of the call stack execution always returns strictly to the caller following the chain of command.
You are ready for this technical assessment. When you sit down in that room, just remember the rules of the road. Read complex expressions from the innermost parentheses outward. Don't rush the math.
And most importantly, use your scratch paper to strictly track every single variable's isolated memory space. Draw those walls. Don't let the kitchen mix with the living room.
Trust the execution flow, trace the processor's path methodically, line by line, jump by jump.
Do not let the exam writers tempt you into skipping steps or making assumptions about the logic. The machine is obedient, you just have to follow its rules. Best of luck on the assessment.
We established right at the top of this session that local variables and parameters are completely and utterly deleted from memory the exact moment a function hits its end statement.
Totally wiped out.
It is a brutal, scorched earth approach to memory management, designed to keep the processor running efficiently. But it raises a fascinating paradox. So as you pick up your notes and head into your exam, ponder this. If a program's fundamental architecture relies on relentlessly wiping its own short-term memory clean after every single modular task, how do you think massive modern software applications like the web browser you use every day or a massive multiplayer video game manage to remember who you are, what's in your shopping cart, and the exact coordinates of where you were standing 3 screens ago? Good luck.